So the purpose of discussing the tight binding model is that we would like to introduce the concept of bands, and through that band magnetism. So if you remember the mental chart that we drew in the other lecture, we would like to talk about Stoner model, which describes band magnetism, but that requires a discussion of the Hubbard model. But the Hubbard model requires a discussion of the tight binding model. So we've already looked at tight binding inside a molecule. Now we would like to look at a chain. Suppose we have a chain of atoms separated by a lattice constant A, and we have n of these atoms, and there is only one, say, orbital per atom, whatever the orbital is. This is just a schematic representation of an orbital, and there is one electron per orbital per unit cell. The unit cell is just one atom. So it's a monatomic chain. Now what we would like to do, if we would like to represent the electrons belonging to an orbital, belonging to an atom by the state n. For example, this could be ket 1, ket 2, ket 3, ket 4, and so on. And if you were to write the Hamiltonian for this system, H, for a single electron, we will have a kinetic energy, of course, K, plus we will have a potential energy term, which is the interaction of the electron with each of the individual nuclei. Correct? So that term could be represented as Vj, where J extends over the chain. Alright. Now we would like to construct a solution to this Hamiltonian. So we propose a solution, and the solution that we propose is psi, which is some superpositions Cn of the n's. And the solution that we propose is of the following form: e raised to power minus I k n a n over under root n, where n is the number of atoms. So this is our ansatz. This is the solution that we propose for the tight binding chain. So the Hamiltonian that we've written over here अभी हम बात करेंगे. Alright, so the Hamiltonian could also be written in the following fashion: K plus Vn. This is the interaction of the electron with the nth atom, plus Vj, where j is not equal to n. This is the interaction of the electron with atoms with other atoms. So we have decomposed the Hamiltonian into this form. So we have decomposed the potential energy terms into one potential energy of the electron interacting with the nth atom, and the electron interacting with all other atoms besides the nth atom. Now, we would also like to assume that all the tight binding atomic orbitals, which are the ket n's, they are orthogonal. Alright. So now what we would like to do, we would like to solve the Schrödinger equation. And we know that the Schrödinger equation is given by Hmn, which is a matrix element of the Hamiltonian acting on Cn, summed over all n's, will give us the energy and Cn. So this is the Schrodinger equation that we would like to solve. For that purpose, we need to find out the matrix elements of the Hamiltonian. Okay? So the matrix elements will be the following. This is M, this is N. So this is one matrix element. So I can write this Ra M K plus Vn plus sum over all of J's. Okay, this is my Hamiltonian and I have N here. Now if I look at the first two terms, this atomic orbital is an eigenstate of K plus Vn with some ground state energy E naught. Alright, just like a hydrogen atom, just like one electron inside coupled to a nucleus. So, but then you have to take the overlap with N. So if I perform this eigenvalue equation so that I have this operator acting on this, then I form the overlap with this, then this will give me E naught only when N equals M. And then I have to include other terms. J is not equal to N, and I have N Vj N. So now I have to see what this term is going to be. The only constraint is that I'm adding up all the terms for which J is not equal to N. Let me raise the voice for this little bit. Hello. Alright. So is this clear up to this point? Now let's explore this term over here. If I look at this term, the overlap of the state M with N connected to this potential energy function. Now remember that J is not equal to N. Now if N equals N, then what I'm talking about is the interaction of an electron that belongs to some atom with another nucleus. So if N equals N, this becomes Vj M. If N equals N. So this is the interaction of the nucleus with some other electron. Interaction of the electron with some other nucleus, because J is not the same as M. So this is like a cross term, V cross. And N, by the way, is not equal. N is equal to N in this case. And none of them is equal to J. थोड़ी सी आवाज ऊंची कर. Alright, so this is a cross term. So if I drew my chain over here, these are the atoms. This term represents an electron that is bound to this nucleus, interacting with some other nucleus. It could be this nucleus, it could be this nucleus, it could be this nucleus. So it's a cross term. Then I could also have terms of another kind in which M is not equal to N, which means that these two indices are different. Then in that case, I am actually talking about a transfer integral, a transfer term between two nuclei. This means that the electron that is on the nth position can hop on to the nth position. For example, I could have a term like this, V get 1, get 2. I could have this term, Now this represents a transfer of the electron, or a hopping of the electron, or a tunneling of the electron from one site to a neighboring site. Now m is not equal to n, and it could be different kinds of m is not equal to n. One possibility is that I only include nearest neighbor interactions. That is, m is not equal to n, but m equals n plus minus 1. So this will give me a certain scalar, a complex number, and I call that complex number minus t. T is a complex number. So in the condition that n is not equal to n, but n equals n plus minus 1, which means I'm allowing hopping between nearest neighbors only, then this mixed term will become minus t. And I will have 0 otherwise. That is, m is not equal to n, and m minus n is greater than 1. That is, I do not allow transfer between non-nearest neighbors. So these are my constraints on the term that I've written at the end. ये nearest neighbor. Okay, for the nearest neighbor, so the electron can hop from this side to this side, which means that this is non-zero. This transfer is non-zero. This term is going to be non-zero. But the electron cannot hop from this side to this side, because the transfer falls off exponentially as you increase the distance between the sides. So these are my constraints on the second term that I've written over there. Now under these constraints, the Hamiltonian Hmn, a particular term of the Hamiltonian will become E naught delta Mn plus this term V cross delta Mn minus T delta Mn plus 1 plus delta Mn minus 1. So this is a term in my Hamiltonian. I can also write this as E naught plus V cross delta Mn minus T delta Mn plus 1 plus delta Mn minus 1. This is called the tight binding Hamiltonian for a chain. Now if you look at this Hamiltonian, this is some constant. This object is some constant. I can also call this constant E naught dash. All right. Now this Hamiltonian is quite interesting. Now that I have the form of the tight binding Hamiltonian, I can use this element to solve the Schrodinger equation with my ansatz, with my trial solution. Yes. Yeah, so I found out an element of the Hamiltonian. If I know the Hamiltonian, I can solve the Schrodinger equation because I would like to find out the dispersion relationship. So this is my Hamiltonian, that's my Schrodinger equation. So I will insert this matrix element into the Schrodinger equation and find out a dispersion relationship. That's what I'm going to do now. So I take the left hand side of the Schrodinger equation. Sum of over n of Hmn, which is E naught prime delta Mn minus T delta Mn plus 1 plus delta Mn minus 1. Now this acts on Cn. Cn, my trial solution, is 1 over under root n e raised to power minus I k n a. This is the coefficient of my trial solution. Alright, now I can solve this. I can expand this with 1 over under root n. I'm taking a sum over all n's. But n, I'm picking up the value of n which is equal to m. So the first term will give me E naught prime E minus I k m a minus t. I'm picking up the value of n which is m equal to m minus 1. So this term becomes e raised to minus I k m minus 1 a. Here I am picking up that value of n which is equal to m plus 1. So I get e minus I k m plus 1 a. See, I'm summing up over all n's, but n must be equal to m, otherwise it's 0. Here n must be equal to m minus 1, otherwise it's 0. Here n must be equal to m plus 1, otherwise it's 0. So I'm just sampling one particular value of n, which has the correct form. So this gives me e raised to minus I k m a over under root n E naught prime minus t E I k a plus E minus I k a. Okay, this gives me E minus I k m a over under root n E naught prime minus 2t cosine of Ka. But this must equal to the right hand side, and the right hand side is simply E times E minus I k m a over under root n, where E is the energy. Hence, I automatically get the dispersion relationship. I compare this E with this. This is my energy as a function of K. So the dispersion relationship for a tight binding chain, E, which is h bar omega, turns out to be E naught prime minus 2t cosine of Ka. This is the dispersion relationship. I can plot this. This is K. Now on this axis, if I were to plot E minus E naught prime, okay, this is just a constant of energy, so it doesn't really matter. So what I would like to plot is E minus E naught prime versus K. I have a cosine of Ka function. And when I make these plots, I plot in the first Brillouin zone. This is pi over A, this is minus pi over A. And when I draw this plot, I get a cosine function which is inverted. I get this. So this represents my dispersion relationship for a tight binding chain. Okay. Now this is something really interesting. Remember, this is the first Brillouin zone. The first Brillouin zone. And these are all the possible K values. And this is how the K, with the K values, the energy is going to change for the system. Now, depending upon the number of electrons that are available, these different K states will be populated. This is called a band. This is a band of K values. and it represents a band of energies. The range of those energies spans from minus 2t to plus 2t within the Brillon zone. So the bandwidth of this band is 4t. This is the spread of this band in units of energy. This is 4t. It's a one-dimensional, so it's 4 times t into 1. For a 2D, it's going to be 8t. For a 3D, it's going to be 12t. So the bandwidth of this band is 4 times t, where t is some hopping parameter. Okay? If t is large, the bandwidth is large. So now a band has formed. And if you look at this band, we can approximate it for long wavelength. We can come up with a nice understanding. If k is small, which means the temperature is low or the wavelength is large for the electrons inside this tight binding chain, then I can replace cosine Ka with cosine Ka will be 1 plus okay, what I could do is the following. So in the long wavelength regime, with Ka is much smaller than 1, I can write the energy as E naught prime minus T2 plus T2 1 minus cosine Ka. So this is just some constant, E naught minus T2. E naught prime minus T2 is just some constant. So this is some constant C plus 2T. 1 minus cosine K is 2 times sine square Ka over 2. This is C plus 4T. Now this term becomes K square A square over 4. So barring this constant factor, the energy is some constant plus K square A square T. So at the bottom of this band, if you look at this band, at the bottom of the band has a parabolic shape. So it's parabolic here, where the energy goes as the square of K. So at the bottom of the band, the energy is parabolic. The dispersion relationship is parabolic. Since it's parabolic, you might assume that you can treat electrons to be free electrons, because free electrons live in parabolic bands with a changed effective mass. We know that for free electrons, the energy is h bar square k square over 2m. So if you were to represent these electrons by free electrons in the long wavelength regime, then we can define an effective mass. Okay? That effective mass turns out to be the following: h bar square k square over 2m star equals k square a square t. So the effective mass is h bar square over 2a square t. So electrons inside the tight binding have an effective mass that is proportional to the inverse of the hopping parameter. It's not a real mass, it's an effective mass. Okay, if the hopping parameter is large, you will have light electrons. The effective mass of those electrons is going to drop. So in a tight binding model, at the bottom of the band, you will have a parabolic dispersion relationship. Alright, now where do we go from here? Now look at this look at this band here. Okay, if I plot the band, it's a cosine curve, particular dispersion relationship. Okay. Phonons will have a certain band structure. Magnons have a certain band structure. In a tight binding model, the electrons will have a certain band structure, and this is what the band structure looks like. Now, this range is from minus pi a to pi a, if this is the k axis. Now, the spacing between two consecutive levels we know is going to be equal to 2 pi over L, because the k value is quantized. Now we would like to find out how many k values exist inside the band. So the number of k values inside the band is 2, this total length is 2 pi over a. So this is 2 pi over a divided by the width of each k value, which is 2 pi over L. This is L over 2 pi. This is L over a, where L is the length of the chain. So what is L over a equal to? L is the length of the chain, A is the size of the unit cell. This is the number of unit cells, the number of atoms inside this chain, N. Now if you have a monovalent atom in which one atom donates one electron, how many electrons can the complete band fill? 2n. Because 2 electrons cannot have the same value of k and have the spin opposite. So if you have a monovalent atom such as sodium, or one valence electron is available, it will only be half filled. Alright? So you get a half filled band for monovalent atoms in this simple model. If you just have one orbital per atom and one electron, you can have as many electrons, but depending upon the kind of the orbital. Okay? So now this band is half filled, so you have a half filled band. Now if you apply an electric field, the electrons can increase their energy in response to the electric field. So remember, this represents a direction. K is a direction. So if you apply an electric field in a particular direction, the electrons can go up here because this region of the band is empty. So the electrons can climb in their energy. So if there are electrons available here and there are nearby unoccupied levels inside the band, the electrons can go there because the electric field is trying to apply a force that's trying to increase the energy of the electrons. So what's going to happen is that just like a snake, this filled portion of the band is going to move downwards from here and it's going to go up over there. So on the two sides of the one-dimensional chain, there is a lowering of the Fermi level here and a raising of the Fermi level here. And because of this difference in Fermi level, the current starts to flow. So when you apply an electric field to a half-filled band, it can conduct electricity. So you have a gradient in the Fermi level. The Fermi level is low here and high here. And the electrons, being negatively charged particles, can go from a low Fermi level to a high Fermi level because they move uphill. Negatively charged particles move uphill. So this is how current flows. And this is where you get a conductor. This is what a conductor is. If on the other hand, you have in this simplistic model in which just one band is available, okay, and you have a divalent atom, so each atom is donating 2 electrons to the orbital. So there are 2n electrons, and there are n k sites, n values of k. So on each k there is going to be 2 electrons with opposite spins to obey the Pauli exclusion principle. So this band is going to be completely filled. Now if you apply an electric field, the electrons don't have any place to go because the band is already completely filled. There is no nearby unoccupied level that's available. So this is what is called a band insulator or an insulator. An insulator is formed. And no conduction can take place. Hall conductivity can take place, but that's a separate issue. So you get a band insulator or an insulator. Now the question is the following. This tight binding chain has given us a band. Alright? Now in the molecule, if you move back to the molecule, to the example of the molecule, and we saw the tight binding Hamiltonian for the molecule, if this is a separation between the nuclei, we know that far away you get the atomic orbitals. Correct? And when you move closer, which means that the overlap T goes up, then you get a level here and you get a level here. One of them you call the bonding molecular orbital, the other you call the anti-bonding molecular orbital. So you get this divergence of energies. Alright? Now in this particular case, you are getting, now there are two possible energies. Here you are getting a spread of energies, a band of energies, because you have a large number of atoms inside the chain. Alright? So remember that as you are decreasing the separation, you are increasing the magnitude of T. So this is what we studied for a molecule. Now let's come back to our chain. Suppose each atom harbors two kinds of orbitals. Alright? Now what's happening in this case here is that you're getting a certain bandwidth of energies, a certain spread of energies. So in this case, what's happening is that if I have the separation on this axis, let's call the separation R. Okay? Now if you far apart, if A is large, which means T is small, if T is really, really small, then this bandwidth, this thing, the 4T is really small. So you do not get any fanning off the energy levels. However, if the atoms get closer together and there are a large number of atoms available, then this unperturbed energy, E naught prime, is going to spread out or fan out into a band of energies. This is going to be equal to 4T. So this bandwidth is 4T. As you decrease the separation, R goes down, T goes up, and the energy spread goes up. So you form a band. This is the case for a single orbital. Suppose that orbital is 2s, is called the 2s orbital. Yes. This is your A here. This is a separation, this is a lattice constant A. Now suppose you have another orbital attached to the same atom. So with each atom there are two orbitals. One is a 2s orbital and the other is a say 2p orbital. The 2p orbital in isolation will have a different energy, probably a higher energy. So when you move these atoms closer together, you decrease the lattice spacing, then this orbital can also fan out and give you a band. So you have this kind of structure. Now, if you are below a certain regime, if the spacing between the atoms is below a certain critical value, some A critical, the 2s and the 2p bands, as they are called, will now overlap. So if I were to draw a graph corresponding to the dispersion relationship that I've drawn over there for this case, for A less than E critical, this is what I would like to draw. The 2s band looks like this, okay, and the 2p band looks like this. Now, if this is the Fermi level over here, if this is my Fermi level, the Fermi level, by the way, could be anywhere, depending upon the number of electrons. Now, if this is my Fermi level, then there are 2s and 2p levels that have the same energy. So the electrons will be shared between the 2s and the 2p valence electrons. So, in other words, the 2s and the 2p bands will be hybridized. So the electrons can share time between the 2s and the 2p bands because both of these bands have the same energy, they are within the same energy structure. So suppose you had this kind of configuration in which the 2s band is completely filled. So the 2s band can be completely filled by 2 electrons. So each atom carries 2 electrons. So if you have the 2s band completely filled, so this is completely filled, you have an insulator up to this point. At this point, at the critical point, the insulator transitions into a metal because now there is a 2p, now the band is all of this. So unoccupied levels become available. So at this point, you have an insulator to metal transition. So you can describe insulator to metal transitions using the tight binding model. So this point represents an insulator to metal transition. All right. Now let's suppose, how do we form band gaps? If you have a chain in which there are 2 kinds of atoms in a unit cell, like a diatomic chain. Then the kind of band structure that emerges if you solve the tight binding model is the following. So this is the k-axis, this is pi over a, this is minus pi over a. Okay. Then at the boundary of the Brillouin zone, a gap opens up. And you get another band. So this is called the extended zone scheme. If you would like to displace these bands through the reciprocal vector, this part will come here and this part will come here, and you can form the reduced zone scheme. So at these edges of the Brillouin zone, these gaps open up. These are called band gaps. Okay? If this band gap is larger than 4 electron volts, generally it's called insulator. If it's less than 4 electron volts, it's generally called a semiconductor. So this is how bands and band gaps are formed. This is a general framework. This is an intuitive picture of how these bands are formed. Now this has implications for magnetism as well. So once we have talked a little bit about the tight binding model, we would like to talk about magnetism now. And we would like to introduce another model on top of the tight binding model, which is called the Hubbard model. Any questions about these points? So far in our discussions, we have ignored the interaction between electrons, right? So the electrons will be attracted to nuclei, but what about the interactions between the electrons themselves? So this gives rise to the physics of correlated electronic systems, which is a very complicated undertaking because it's a many-body physics problem, and it also forms the basis of the application of quantum field theory in condensed matter systems. And we can also use the second quantization formalism to discuss the Hubbard model, and probably I'm going to upload those notes as an A site for you to study. However, what we would like to introduce now is some kind of interaction between the electrons on top of the tight binding model. One model that's proposed is the Hubbard model. Alright. Suppose that the number of electrons per site is x. Alright. Per site inside the band. We know that if x is less than 2, we have a metal. For x equals 2, we have an insulator. Alright. Now, this also means that x over 2 gives us the fractional filling of the band. If x equals 2, the band is completely filled. If x equals 0, the band is empty. If x is 1, the band is half filled. So when the band is half filled, we have a situation like this. So for each band, we define an x, which is the average number of electrons on a particular site. Now the Hubbard model would like to introduce interactions between the electrons. Alright? So we have a new Hamiltonian. The new Hamiltonian is a sum of the tight binding Hamiltonian, which I call H naught. Alright? Plus some Hamiltonian that is specific to the Hubbard model, which talks about interactions between the electrons. Now this Hamiltonian has an expectation value. That expectation value is plotted here on these graphs. Now this can be thought of as a kinetic energy of the electron, because it talks about the transfer of electrons, the hopping of electrons from one site to another. Of course, it has a potential energy, the interaction of the electron with the nucleus, but if an electron goes to high energy levels, its kinetic energy is going up. So the expectation value of this H naught is generally referred to as the kinetic energy of the electrons. Okay? So you don't want to raise the kinetic energy of the system. So if an electron goes to higher and higher levels, the total energy of the system is going up. Okay? So if you want ferromagnetism in your material, due to these itinerant electrons, due to these valence electrons that are a part of the sea of electrons, that are inside the band, in the conduction band, if you would like, ferromagnetism, then all of these electrons must have spins that are parallel. But if these spins are parallel, they cannot be on the same side, because that is disallowed by Pauli's union principle. So if those spins want to be parallel, you would like to have a magnetization, then the kinetic energy of the system is going to be really high. This means that ferromagnetism is a highly unfavorable circumstance because that raises the kinetic energy of the band electrons. Do you agree with me on that? Because in ferromagnetism, you have a magnetized sample, all the spins are parallel. So they must be on different sides, otherwise the Pauli exclusion principle will be jeopardized. So you want the spins to be parallel, they must be on different sides. And if they are on different sides, then it raises the kinetic energy of the system. Because they have to go to different K values. They must have different K values then. Because when they are on the same side, they have the same K value, they will have opposite spins. So the energy of the system is going up, which means that due to purely energetic considerations, if you don't take into account any interactions, there can be no ferromagnet. So now Hubbard's model resolves this anomaly. What Hubbard proposed is a Hamiltonian, H Hubbard, which is given by Ni plus spin up, Ni spin minus, sum over all the sides. This is Hubbard's proposal. It's a model, so it's a proposal. What does this mean? And a certain parameter u, okay, a certain constant u. What does this mean? Ni plus or Ni up is the number of electrons will spin up on side I. Okay? This is the number of electrons on side I will spin down. So you multiply the two. This is like an interaction between the electrons. When you talk about electrostatic repulsion between electrons, you have an E squared over 4 pi epsilon naught R term. Or you multiply the two charge densities. So this is like a Coulombic repulsion between the two electrons. This term represents the strength of the Coulombic interaction between the two electrons. So if this is large and if this is large, then the two electrons are on the same side, which means that the energy of the system is going to go up. So this term actually wants the electrons to disperse. It would like the electrons to minimize their energy by delocalizing. This term does not want the electrons to delocalize. So there is a competition between the kinetic energy and the interaction between any two electrons. Alright? So the overall energy has to be minimized. And we would like to see if the Hubbard model can give rise to magnetism. You see, one thing I would like to mention here, it's a slightly advanced concept. It's one of the most advanced concepts in our course. When we're discussing polyparamagnetism, free electrons, if this is my density of states, GE, this is my energy. When we talk about polyelectrons or electrons that are free, this is the Fermi energy, EF. We have alpha or up spins and we have beta minus spins. In the absence of a magnetic field, both of these spin subbands have the same energy. Correct? So the material is not magnetic. It does not have a magnetic moment. And remember, when we apply the magnetic field, the spins that are favorably aligned, their energy gets lower. So this band shifts lower, it goes down. And this band, which has the spins aligned in the wrong direction, goes up. So now you have a configuration in which there are more alpha spins than there are beta spins. And if you remember, this spacing is given by 2 mu b b. And from here we were able to calculate the susceptibility, which was called the polysusceptibility. So when you apply a magnetic field and you have these free wandering itinerant electrons, you can get a paramagnetic term. This is called the polyparamagnetism. But in ferromagnets, you can have spontaneous magnetism. As we studied from the Weiss molecular field theory, you can have magnetization spontaneously inside this, even in the absence of a magnetic field. So how do we explain this? The Hubbard model helps us explain this. Okay, so now we would like to find out why is iron magnetic, why is cobalt magnetic, and we would like to use the Hubbard model for that purpose. Okay, so this is the Hubbard Hamiltonian, the proposed Hubbard Hamiltonian. The question is, how could we get a shifting of the spin subbands or the spontaneous splitting of the spin subbands in a ferromagnet, even in the absence of a magnetic field? There has to be some correlation between the electrons, some interaction between the electrons. All right. Now I've already described that if I have a perfectly saturated ferromagnet, it's a spin polarized state. All the electrons have spins that are parallel. Let's call the quantum state for such a ferromagnet C psi polarized. Now if I were to calculate the expectation value of the Hubbard Hamiltonian for such a state, 100% polarized state, what is this expectation value going to be? This must be 0 because this term is 0. The two electrons, any two electrons are parallel, so they can never be on the same side, otherwise Pauli-Exclusion principle is going to be violated. So this term is always 0 for any pair of electrons in a perfectly polarized state, so this must be equal to 0. But that's going to increase the energy of the system. The H0 is going to go up because now the electrons are on different sides. They will have different K values. They cannot have the same K value because having the same value will force the spins to be opposite. So they have all the spread of K values that are available in the band. So the kinetic energy of the system is going up. So why is this polarized state doesn't exist in the first place? Okay, so there is a competition between the kinetic energy and the correlation between the electrons. One is trying to increase the energy, the other is trying to lower the energy. We would like the overall energy to go down. That's what we would like to do. So we start our discussion from this Hubbard Hamiltonian and see how this can be achieved. So if you look at the Hubbard Hamiltonian, I'll write this as HH. This is U Ni, okay, over all I. Now I can write this in the following form: U over 4 Ni plus Ni minus squared minus Ni plus minus Ni minus squared for all time. Okay, I just do an algebraic manipulation. And this equals this thing. Alpha squared plus beta squared, 2 alpha beta. This is alpha squared plus beta squared minus 2 alpha beta. So if I construct this sum, I get this. Now in the next step, I would like to apply a mean field approximation. A mean field approximation means that I would like to replace these remember in the quantum field theory these are really operators, right? So I would like to replace these numbers by their average values. This is a mean field approximation. When you replace a number by an average value. Okay. So I write this as u over 4. I get rid of this sigma sign because I'm doing a mean field approximation, and I replace this with its average, ni plus ni minus whole square. And I don't need the i's here. Minus now what is this equal to? This is the average number of electrons per site, ni plus, irrespective of the spin. So this is just x. Okay, so this thing is just x as I have defined it. This is the average number of electrons per site. Now this number here, it's the average difference between the spins that are pointing up and the spins that are pointing down. What is this related to? What is this average number related to in magnetic terms? Yeah, spin up, spin down. If this is 0, the sample will be unmagnetized. If this is large, the sample will be magnetized. So this is really going to be proportional to the magnetization of the sample. Correct? Hence, I would like to write this in terms of the magnetization. The magnetization is, if I'm talking about spin half particles, I'm taking G to be 2. So I get mu b is the moment of each spin into n plus minus n minus. This is the net polarization, the difference between spin up and spin down on average, multiplied by the moment of each divided by some volume. Now, this volume is the volume of the unit cell. Okay, so I call it small v. Okay, because each unit cell has one site. Each unit cell has one site. This is the magnetization. Alright. Now this means that now this object is the energy of a single site. The Hubbard energy of a single site. So if I would like to find out the total energy of the system, the Hubbard energy of the system, total, then I would like to find out how many sites are available. The number of sites that is available is the volume of the material divided by the volume of the unit cell. This will give me the number of sites. So I multiply this object with this thing over here, which is the energy of each site. That is u over 4 x square minus. Now this is object is n small v over mu v square. This is the energy due to the interaction between the electrons inside the total volume of the material. Small v is the size of the unit cell, capital V is the total volume of the material. Now, interestingly, if the magnetization goes up, then this term decreases, the energy goes down. So this Hubbard Hamiltonian is of the right form. If the sample gets magnetized, then the energy of the system goes down. So there is one H naught tight binding Hamiltonian which likes to increase the energy of the system. This energy would like to go down if the sample gets magnetized. So if M goes up, this is negative here, then the overall Hubbard energy, the energy associated with the interaction of the electron, goes down. So if we include these interactions inside the system, then we might expect to get non-zero magnetization even in the absence of a magnetic field. Alright? Yes? Yes, so there's a competition. No, there's a competition. So what we would like to minimize is the kinetic energy plus the energy associated with the Hubbard interaction. This is our total energy, and we would like to minimize this. Alright, so this gives rise to, so now that we will introduce the Hubbard model, we would like to introduce the next model, which probably we do in our last class on Wednesday, which is the Stoner model. Based upon this, we would like to see how this model can give rise to magnetization for certain elements, and for certain elements it does not give rise to magnetization. Why are iron, cobalt and nickel in the 3D series only the elements that can give rise to spontaneous magnetization? Alright. So this finishes our discussion of the tight binding model and the kind of Hubbard Hamiltonian that I wanted to introduce. The key is that the kinetic energy of the system goes up if the sample gets magnetized, because the spins are now parallel. Naively, you never expect a sample to get magnetized because that increases the energy of the system. But the Hubbard model comes to our rescue. The Hubbard model says that there are interactions between the electrons, a Coulombic repulsion between the electrons. That Hamiltonian is cast in the form of a model. That model tells us that if the magnetization goes up, the energy associated with the interaction between the electrons actually goes down. So there is some ray of hope. We would like to see where is the balance, and why does the balance tip in the favor of ferromagnetism for some elements and it tips against ferromagnetism for other elements inside the 3D series. Then we would like to answer, why does iron have a non-integer magnetic moment for formula unit 2.2 μb? Why is that the case? In fact, this Hubbard Hamiltonian can also describe super exchange, direct exchange, all kinds of exchange interactions, all kinds of ferromagnetic exchanges. But this is something beyond the scope of this course because we really need the second quantization formalism for that. Anyway, we'll get a good idea of why iron, cobalt and nickel is magnetic based upon the Stoner criterion which derives from this Hubbard model. So on Wednesday we're going to have our last class, inshallah, and I've uploaded one homework. Start early with the homework, it's a lengthy homework. Inshallah, see you on Wednesday. Yes?
Why was the electrostatic repulsion between the electrons equal? What was the assumption there?
Because it's an independent electron model. The tight binding model by its very design is an independent electron model. It does not take into account the correlation, so you have to add on those correlations. Okay.
Should we already have, because that is the physical reality?
So you start with simple models and then you add on more complications, you get closer to reality and successively more sophisticated models. You have to minimize this energy with respect to M, with respect to X. You fix X and you minimize with respect to M. Alright. वाली भी शायद लगा दे। मॉडल की थ्योरी, मॉडल एक मैथमेटिकल थ्योरी जो प्रपोज की जाती है किसी फिनोमेनन को। मॉडल की थ्योरी
जफर साहब, सर प्लीज़ वीडियो ले ले। यूएसबी है आपके पास?